Hello, welcome everyone. I'm starting to regret having agreed to being recorded, but that's fine. Let's see how things go. So I have a very simple plan for my 3 lectures plus 1. The first lecture is what? The second lecture is how. The third, actually it's the TA, and it's Livio who's gonna do that. Livio, say hi. Livio is there. And he's gonna tell you, well, do something. And then the fourth lecture, which is again me, is maybe the why. So pedagogically, maybe this is not gonna be the best, but we'll see. So, what are we gonna talk about? Well, you all know, we've seen today, actually, in definition, a knot is an element of pi 0 of embedding of S1 into S3. But yeah, it's a rather maybe convoluted definition. So a knot is an embedding of S1 into S3, or maybe the image of, up to ambient isotopy, and this is maybe a bit of a subtle point, which is going to play a bit of a role. I want this ambient isotopy also to fix the orientation of the embedding. And we care about knots to up to isotopy, ambient isotopy. And we have some examples of knots. So if I take a 2-plane in R3 or S3, and I take a circle inside it, this is the simplest knot you can think about, the simplest embedding you can think about, and this is the unknot. Very fundamental example. And the maybe main example that we're gonna see during these lectures. So this is example 1, maybe example 2, is torus knots. I should do a bit bigger, right, Dave? I'll try. So what is a torus knot? I take the standardly embedded 2 torus in S3. I take 2 curves on the torus that I call the longitude and the meridian, and I want to orient them according to the right-hand rule. And a torus knot, the torus knot TPQ, is a curve of slope P over Q measured in the basis lambda mu of H1 of T2. Actually, let me call this just T. What does this mean? We take a curve that winds around, maybe being of slope P over Q means this is P lambda plus Q mu. It means I take any curve in the homology class P lambda plus Q mu. There is one such curve up to isotopy, and this curve, I'm gonna call it torus knot. I'm being a bit sloppy here. To have a homology class, I need to fix an orientation. The slope does not see the orientation. So technically there's an exercise behind this. Is that if I take the curve of slope P lambda plus Q mu, this is the same any curve. If I take a curve in this homology class, or if I take a curve in the homology class minus p mu plus minus q mu, these are actually the same knot. In other words, if I reverse the orientation of a torus knot, I get the same torus knot as an oriented object. It's a very complicated way of saying this, but and actually, to tie with the last word in the title, complex singularities, torus knots are a special case of a broader family of knots that are called algebraic knots. Actually, not everybody agrees on terminology, but let's stick that algebraic knots are links of singularities. And what are these? I'm going to use sort of interchangeably the two words, the two formulations. So what are these? I take a function or a polynomial in two variables. I'm going to assume that f of 0, 0 is 0. And I'm going to look at its set of zeros. So this is the set of pairs x, y for which fx of y vanishes. And I'm going to do something that is maybe a bit bizarre. I'm going to take a sphere of radius epsilon, centered at the origin. And I'm going to intersect it with v of f. So I'm going to use the notation k of f or k of f0. This is the intersection of S3 of radius epsilon with v of f for some epsilon sufficiently small. And the notation suggests that this is a knot or a link. This is embedded in some S3 of radius epsilon. And actually, if epsilon is very small, the intersection is transverse. So I'm intersecting a codimension 1 object and a codimension 2 object, and I get something of codimension 2 in here. So it's actually a knot or a link. It's a union of S1s. And independent of epsilon. Meaning up to isotopy I get the same object. So this object is intrinsically associated to f and the point 0, 0 that I've chosen. So this is called the link of the singularity of f at 0, 0. And in fact, both examples that we've seen arise in this fashion. The unknot arises when I pick f to be just a linear function, and torus knots exercise TPQ comes from f equal xp plus yq. Maybe I should have said, that when I write slope p over q, I'm implicitly assuming that p and q are coprime. So I'm actually looking at knots and not links. But yeah, so maybe let me write it down. And I want p and q. Great, so these are the main objects that we'll be working with for the next few days. And the motivation for why we work on them is that, to me, these are the most natural examples of knots that you can have. They arise in a very natural fashion from algebraic geometry, and moreover, they can be generalized to higher dimensions, as maybe we'll see later today. or maybe not. So,
are you assuming it's isolated singularities?
Yes. I am sweeping a few things under the rug, but I'm assuming that f is reduced. Actually, it doesn't really matter. For curved singularities, I don't think it matters. But let's assume that it has no square factors, and then it's enough.
I wasn't wondering what that is. I was just wondering whether the singularity is isolated.
It's automatically isolated if the polynomial is reduced, because we're in C2, so it's a curve, and singularities on a curve are either the whole curve or a point on the curve. On surfaces, you can have singularities along a curve, but on a curve, you can have singularities along points or along whole components. But thanks. Yeah, that's. I'm gonna be a bit sloppy, but that's okay. It's good to have Gregor here who picks up on my sloppiness. So, what's maybe the goal of knot theory? The goal of knot theory is to classify knots. And this is hard. And people have been at it for, 150 to 100 years, and it's hard. So maybe we want to be a bit less ambitious, and we want to somehow look at knots up to some less restrictive equivalence relation than isotropy, and this is what we're going to look into. But first, I want to define two operations on knots. If I have K and K prime, 2, and let me state it here, oriented knots, I can form that connected sum. This is somewhat similar to what Danica was saying at the beginning of her talk. A knot I can view both as an embedding of an S1 or as an embedding of an arc relative to a disk. And this is the key to defining what a connected sum is. I can standardize my two knots in a ball. So I have K here, and I have K prime here, and they're somewhat standard in a ball. And what I'm doing is I'm just excising what happens in the uninteresting or in the standard part, and I'm gluing them together. In this way, and secretly, I'm using the orientation to decide which way I'm doing the connected sum. I want to connect some things coherently so that when I run along my knots, the orientations match up. And maybe the other operation that I can do on knots is the mirroring. So if I have a knot, K, I can look at its mirror. If this is the set, let's say that this is the set of points xt, yt, zt in R3, I'm removing a point from S3 and just putting everything in S3, then M of K is just a set of points xt, yt, minus zt. Usually, I can pick any orientation reversing diffeomorphism of the ambient space, and I get the same knot. And again, there's an orientation that is preserved here. I'm thinking of running along K in a certain direction, and I'm thinking about running along the mirror of K in somehow the same direction. Good. It's nice to have operations on a space. It would be nice on a class of objects, it would be nice if these objects would behave well with respect to these operations. And it's easy to see that the connected sum that I'm gonna denote with a sharp sign, this is well defined, it's associative, it's commutative, but it has no inverse. And it's easy to see that the mirror is just an involution. And somehow, I don't know, we would like to have a simpler, well, a less strict, a less fine equivalence relation on knots. And simultaneously, this equivalence relation will also make these operations nicer on knots. So let me define what a concordance is. Let me say from K0 to K1, 2 knots is an embedding of 0, 1 times S1 in 0, 1 times S3. And in here I have two embeddings, 0 times S1 and 1 times S1. And I want that these two embeddings go onto 0 times K0 and 1 times K1. And they're both embedded in here. This is maybe the worst definition you've ever seen of concordance. Let's draw a picture, which is maybe a bit more useful. What is happening? I have S3 times the interval. This is my interval direction, 0, 1 maybe. This is my S3 direction. And in here, I have my wonderful first knot, K0. In here, I have my second equally wonderful knot, K1. And in between, I have some embedding of the annulus that does possibly weird things. And it's easy to check that K having a concordance to K1 is an equivalence relation. Why? Because I can simply stack up knots. And also, it's easy to see. Maybe I want to prove this at some point. Do I want to prove this? Yeah, maybe I want to say something about this a bit later. Let me just say another definition. So a knot K is slice. I think you've seen one definition of being sliced this morning, and I'm going to give an equivalent definition now. Is slice if it is concordant to the unknot. Why is this equivalent to Jeff's definition from this morning? If you have the unknot you can always cap off with a disk in S3, and then if you have a disk in S3, well, you have a disk in B4 as well. So, great. So we have an equivalence relation, which is finer than, well, it's coarser than isotopy, as Jeff has shown you this morning, because he's shown you some knots that are slice, but that are not the unknot. So there are more knots that are slice, that are equivalent to the unknot, than there are knots that are isotopic to the unknot. So we've done some simplification on our space of objects that we want to classify. So maybe there's some hope of saying something more about these classes. So the new question becomes classify knots up to concordance. This is still hard, but people have been at it for a while now, and it's not like we know, well, we know quite a bit, but not everything yet. And what's the catch? The catch is that maybe the following proposition, knots up to concordance still have an operation defined by the connected sum. I'm going to get there, 1 sec. This is an abelian group. So if we mod out by this bigger equivalence relation, we gain a lot of structure on the space of objects that we want to study.
Shouldn't we take the mirror perfection from K1?
So far, I have not mixed mirrors with concordance. I'm going to do it in a second. But so far, these are two separate things. Mirror is an operation that I have on knots, and concordance is an equivalence relation.
Yeah, but I don't think any knot is concordant to itself like this.
Yes, it is. Oh, I see what you mean. It depends on which orientation you're putting on the S3 that you're considering. I'm orienting the lower S3 with the inner normal and the upper S3 with the outer normal. I know. It's painful, but that's what it is. I feel your pain. So the question is that, maybe I should repeat the question. The question is that there's some orientation issue that I'm not sweeping under the rug, but this 0 times S3 has two different orientations. One as the oriented boundary of this oriented manifold, and one as 0 times an oriented manifold. So point times an oriented manifold. And these two orientations are not the same. They're opposite to each other. And when I'm thinking of 0 times K0, I'm thinking about this knot as sitting in the 0 times S3, oriented as point times S3. Basically, this solves the question of saying that K0 is concordant to K0, because I can just take the product concordance. That's the easiest, the simplest concordance you can think of. Similarly, if you have an isotopy between two knots, you can plot this isotopy and you get a concordance between two knots that are isotopic. That's a good question. The other good question that has not been asked, and that I've been really avoiding so far, is in which category am I working? Because implicitly, I'm a smooth topologist. Apologies to the people who do some locally flat stuff that I think are concentrated over there. I'm always thinking about smooth embeddings. So smooth knots, smoothly embedded knots, smooth concordances, and I'm thinking about everything in the smooth category. Most of what I will say during these lectures works in both categories, but I'm more comfortable working with smooth stuff. So whatever I say is smooth. Great. So I guess you all agree that having a group structure on an object is good because it helps you classify things, especially if it's an abelian group. And this is worthy of a definition, so the concordance group C is just this group. And if you want to have a group, you better have an inverse. So maybe let me say something about the proof of this proposition. Maybe a sketch of the proof. So what is happening? I want to say that if I have two knots, so what do I need to prove? So we already know that connected sum is associative and commutative. We just need to show that if I need to show that if K0 is concordant to K0 prime and K1 is concordant to K1 prime, then K0 connected sum K0 prime is concordant to K1 connected sum K1 prime. And I need to show that there's an inverse. So let me just sketch a proof for both things instead of actually proving anything today. But if I have a concordance from, did I screwed up my notation? I want this K1 and this K0 prime. So if I have a concordance from K0 to K1, remember that if I want to do the connected sum, I need to find a small disk in which my knots are standard. And what I want to do is I want to say that if I have a concordance from K0 to K1, I can actually straighten this standard disk to have a standard disk times an interval in which everything is standard. And I can do the same for K1 and K1 prime, K0 prime and K1 prime. And what I'm doing is I'm doing a connected sum just along these arcs. One way of seeing this is I can remove a neighborhood of this or a neighborhood of this, and I can glue them together. And the one thing that I need to check is that there is no knotting in dimension 4. These two arcs, any two arcs that I pick are actually isotopic. And this is what Danica was also saying earlier, there's no knotting in dimension 4. No knotting of arcs in dimension 4. So I can do a connected sum of two concordances which proves that this is well defined. So concordance commutes with taking concordances. Connected sum commutes with concordances. And the existence of the inverse is related to Ludovico? Lorenzo's question. To Lorenzo's question, it's roughly the same picture actually. But I need to show that there is a knot K, that there is another knot. If I'm given a knot K, I need to find an inverse. And actually the answer is in the stupidest picture you can think of. You take the product of K with the interval, you take the trivial concordance from the knot to itself, and you carve a path. Wait, are you carving a path? No, you're not carving a path. Sorry. You're not carving a path. Forget this picture. You take your knot, you take your standard disk here, you remove it, and you get an arc, or what's called a tangle, in B3. And then you spin this thing around. When you spin this thing around, you're sweeping an arc in B4 relative to its endpoints, And when you sweep an arc relative to its endpoints, this is similar to the picture that Danica had here. You have a 2-disk which is embedded in B4. And when you do this, you actually see that whatever you have on the boundary of your B4 is the union of K minus a standard disk and something else. And the something else happens to be the orientation reversal of the mirror of K. You are flipping your knot K upside down, and you're also running along it in the opposite direction because you want to match the orientation of K. So the catch of this is that minus the mirror of K is an inverse of K. So we've proven that the connected sum is well defined. It goes down to an operation on the concordance, and that we have an inverse. So we have a group. Yes, but I've told you that, yeah, it's an equivalent definition to what Jeff gave you this morning. You can now remove a small ball here, small 4 ball in there that is standard, and you get a concordance to the end node. But yes, you're right. Good. More questions? Right. So, what is an annulus? An annulus is a surface with 2 boundary components and genus 0. Why stick to genus 0 necessarily? Maybe there's something else to be said when we look at surfaces of higher genus. So let's actually look at what happens in that case. So the cobordism between 2 knots K0, K1 is an embedding. And let me not write down everything somewhat precisely, but I have a surface of some genus that is embedded in S3 times the interval, or interval times S3. And I want that the lower part is mapped to K0, the upper part is mapped to K1, and in between it does a bit of whatever it wants. And the remark is that any 2 knots are cobordant. Given any 2 knots, I can always find a surface that interpolates between. You can think about why, but there are many different proofs for that. But this allows us to say, to measure how distant 2 knots are. So the cobordism distance, d cob, K0, K1 between 2 knots. Is the minimal genus of a cobordism between them. Why is this in any way good? Well, it's good, for instance, because it induces a metric. Maybe an exercise induces a metric on the concordance group. The essentially the only thing that you need to show is that the triangle inequality is satisfied. That's believable. I can always stack two cobordisms together. The genus adds up. This might not be minimal, but it gives you an upper bound. And the only things that are distance 0 are the same things. And this is exactly the definition of being at distance 0. It's exactly the same definition as being concordant too. So it induces a metric and not a pseudometric. Right. So let me get to the question that I really want to think about. I defined for you a class of objects that arise, we somehow all agree, somewhat naturally from a different subject. And I've introduced an equivalence relation between knots and a group of knots somehow. And I kind of want to know how these two things interact. So what can we say about algebraic knots? Up to concordance. Or maybe bonus question, what is the cobordism distance on algebraic knots? And if you want to know why, you have to wait until Thursday. But I promise that I will give you some motivation for looking at these objects. And it's not just randomly picking two concepts and mixing them together. I swear that there's something behind this. So let me mention one theorem. That's due to Litherland from 1979. Torus knots are linearly independent. In C, no protests. 1. This cannot be true in general, because if I have a positive torus knot and its mirror, well, they are both torus knots, but one of them is opposite to the other. So this cannot be true unless I specify something more. So I need to say positive torus knots, where positive refers to P over Q being positive. So maybe let me write it here. And these are exactly the knots that come up as algebraic knots. In fact, when I wrote here in the exercise, TPQ comes from f equal x to the p plus y to the q, in order for that expression to make sense, or in order for that expression to be a polynomial, I better have p and q both positive. So p over q is positive, so the only knots, torus knots that can arise from singularities are positive torus knots. And actually all of them arise from that. And the conjecture that I wish I could prove, but no way, due to Rudolph. I don't know when from, but around the early 80s, I would say, is that algebraic knots are linearly independent in C. Yes? Oh, I thought it was the other way around. Okay. When? Okay. 74, 75? Let's put 75. Thanks, Livio. It's good to have a good TA. It's very important. Right. And this conjecture has motivated really a lot of research. There are fairly recent papers that address some very specific cases of this conjecture. So, and as I said, the why and the how are going to be pushed to tomorrow and to Thursday. And today it's mostly what. So what I would like to do now is to switch gears and talk a bit about algebraic knots. And yes?
Should there be a sign there?
No. No, because algebraic knots are, to me, algebraic knots are positive. So positive torus knots are algebraic, negative torus knots are not. So that clears exactly that ambiguity between positive and negative.
In dimension 3, they generate all the torus.
Say it again?
In dimension 3, algebraic knots is generated by all the positive torus.
In some sense, yes. This is exactly what we're going to see now. I'm going to take a closer look at what algebraic knots look like. Great. So we're going back to the 30s now. Well, 20s actually. So algebraic knots. So there's a theorem of Browner. I think it's 28 that exactly classifies which isotopic classes of knots arise as algebraic knots. And my former postdoc, Oz Shavk, really pushed for me to say that you should look at Milner's book on complex hypersurface singularities for a better reference. And maybe there's also the book by Briskorn and Knurrer, which has really beautiful pictures, and it's a fun book to read. It's maybe hard to find information. There's a lot of information, and there's also Wall's book, same Wall, different book, on complex curve singularities that also has a lot of information. It's a bit more concise and less beautiful pictures, but it's a very good book. So let me drop some references here. So what's the theorem? Algebraic knots are iterated torus knots and all sufficiently positive iterated torus knots, let me abbreviate this with ITK, are algebraic. I've stated a theorem that makes no sense, so let me define what I mean by iterated torus knot. So I need to define what a cable is. So given K in S3, any knot, and two parameters R and S, co-prime integers. And let me write GCD. Co-prime integers. I can sort of play the same construction that I've done for torus knots all the way up there, but instead of playing it on the standardly embedded donut-shaped torus in S3, I played it around a knotted torus, and this torus is knotted precisely along K. So I can take the boundary of the tubular neighborhood of K. Let's say the closed tubular neighborhood to make Danica happy. So this is the boundary of a closed tubular neighborhood. Okay. And in order to play that game, I need to tell you with respect to which curves I'm measuring the slopes. So I need two curves on, let me call this tk, just to introduce more notation. On tk, I have one that is the meridian of k. So what is tk? Tk is an embedded, tk is the boundary of a solid torus that is embedded in S3, whose core is the knot. So in this solid torus, I have one disk, which is a disk that meets k. Well, I have infinitely many, but they're all isotopic. There's a disk that meets k at one point, and that goes all the way out to the boundary. This is called the meridian disk. And the boundary of this curve, I'm going to call the meridian of k. And then I need a curve in the other direction. I want a curve that meets mu once. And of course, I swapped colors with respect to what was there, but you'll bear with me. Lambda of k. So mu of k, this bounds a disk near k, or transverse to k. And lambda of k, we cannot ask for it to bound the disk, but we want that it bounds the surface in the complement of k. And there is exactly one such curve up to isotopy. I'm not going to prove it, but maybe I'll drop it on Livio to do that, just because he doesn't have enough stuff to do already. And this gives me a basis for h1 of tk, with respect to which I can play the same game.
But you have to somehow tell us how you orient.
Yes, I need to orient them. And I can orient lambda consistently with k. So lambda will be homologous to k inside the neighborhood. It will actually be isotopic to k inside the neighborhood. And since k is oriented, lambda is also oriented. And I want to orient mu of k so that it's oriented as the boundary of the disk, and the intersection, the oriented intersection between the disk and k is 1. I'm sweeping all of this under the rug. It's kind of essential because I'm talking about positive versus negative, but there is one consistent way of orienting things, which is also the right-hand rule. So lambda you orient like k, and mu you orient so that when you run along k, your lambda goes like your right hand.
So the linking number between mu and
k is 1, yes. Except that I haven't defined linking number, but yeah. But that's it. And so this gives me a way of parameterizing the boundary. So it gives me a way of saying what a curve of slope R over S is. There's some extra care to be taken because their orientations did not matter so much. Here, I actually need orientations somehow. But again, I'm sweeping some things under the rug, but not too much. So the RS cable of K is the curve of slope R over S. Wait, now I need to be careful. I want to run R times along lambda and S times along mu on tk. So in particular example, if I do the one, I will denote this with KRS. If I do K1 anything, this is isotopic to K. This is the convention that I want to have. Cool. What does sufficiently positive mean? Okay, what is an iterated torus knot? So an iterated torus knot is an iterated cable. It's a cable of a cable of a cable of the unknown. So it's something that will look like a knot, P1, Q1, P2, Q2, and so on, Pn, Qn. So this is the Pn, Qn cable of whatever is there before. So I played this game of Russian dolls somehow with the neighborhoods of the knots, and I keep threading curves in these, on the boundaries of these neighborhoods. So for instance, TPQ, this is the PQ cable of the unknown, pretty much by definition. Right. Now I blame Dave for making me write too big, so I have to erase the blackboard. So almost everything is defined in the statement of Browner's theorem, except for what sufficiently positive means. And this is related to some of the questions that were there earlier about positive torus knots, negative torus knots. So an iterated torus knot is sufficiently positive if so P1, Q1 are both positive. This covers the case of torus knots. The first knot that we start off must be a positive torus knot. And then Pk is positive for all k, and Qk plus 1 has to be larger than Pk, Qk, Pk plus 1. Lots and lots of words. Example. If I start with the trefoil, T23. Sorry, let me use the notation. So, T23 is fine. T23, this is a trefoil, and I take the two K cables. This is algebraic if and only if K is at least 13. And in fact, I can even give you an explicit complex function whose link is precisely this knot here.
So Browner's theorem says algebraic if and only is sufficiently positive?
Yeah.
Not sure that's fine.
Algebraic knots are iterated torus knots, and all sufficiently positive iterated torus knots are algebraic.
I guess you didn't
Yes.
write that algebraic knots are always sufficiently positive.
Yeah, I did not write it in the first line, which is why I had to explain. Yeah. If you want algebraic if and only if sufficiently positive ITK.
So it isn't if and only if.
Yes, I mean, depend.
Our claim is that.
Yes, the second sentence is an if and only if.
And is there any way to remember this formula?
Yes, you remember this example.
But Qk, if I divide by Pk plus 1, it still doesn't make any sense.
Why? So the way I remember it is by remembering this example. I know that the first two something cable of the trefoil, which is algebraic, is the 213 cable. And I know that there's something has this form, more or less. I have no better mnemonics than this. Right. Let me, in the last 4 minutes, let me say some general things about links of singularities, but restricting to knots somehow. So, as a theorem, due to Milnor, Le, maybe it was also known for curves a bit earlier, but there are more general theorems than what I'm stating. But if I have f as above, I told you that to look for a torus for an algebraic knot, I need to take a small ball of a small sphere of radius epsilon. Actually, this sphere is the boundary of a small ball of radius epsilon. So I can look at B for epsilon inside C2, and I can look at its intersection with VF, and I can actually look at the exterior. Let me call it EF. This is B for epsilon minus VF. And somehow this is a manifold with corners, more or less, and with boundary and corners. But there is a fibration. So I need to be careful about this. So the exterior of F fibers over a small disk minus the origin, D2 minus the origin. And there's also the exterior of the knot that lives somehow, is one of the halves of the boundary of the exterior of F. This fibers over S1 of radius eta, which is included here. And the fiber is a surface that's called the Milnor fiber. What am I saying? I'm saying that I have my function f. This is a 4-ball of radius epsilon in C2. This is the zero set of f. If I remove the zero set of f, I have a fibration by objects that are somehow close to my zero set, but they are surfaces. Now they are surfaces with boundary. And what I'm saying is that this fibration that I have on the complement of VF inside the 4-ball actually restricts to a fibration of the boundary S3 minus the knot. In other words, one different way of saying this for those of you who have seen fiber knots. Jeff, did you find fiber knots this morning?
No, but I'm going to.
Okay, great. So tomorrow?
Maybe Thursday.
Okay, so on Thursday at the latest, you'll find out that this implies that K of F is a fiber knot. And actually, there's a lot of theory behind fiber knots. You know that for a fiber knot, the surface that it bounds minimizes its genus as a surface in S3. And I guess that a lot of what Jeff is going to talk about is comparing what happens between when you pass to B4 and looking at the slice genus of these objects. And it turns out that for algebraic knots, this was one of the biggest results that people did with gauge theory some 30 years ago, is to prove that actually these surfaces are genus minimizing in B4. So these gadgets that, again, pop up quite naturally from the complex perspective are interesting from the topological perspective. And I don't have time to say what I wanted to say in the last third of the lecture, but a lot of what I said carries over to higher dimension. Not everything, but a lot of what I said does. And anyway, I'm over time, and I'm going to stop here. Oh, I can also repeat the question if you want.
I was not anticipating a microphone. So the Milner fiber is genus minimizing. Does it also minimize the cobordism distance to the unknot?
Yes, it's genus minimizing in S3. This is true of all fibered knots, but there are fibered knots for which the genus drops dramatically.
Okay.
For instance, if you take a knot and its mirror, they're both fibered. Their connected sum is also fibered, but then it slices. So the surface that you obtain from the two fibers is genus minimizing in S3, but somehow what is surprising is that it stays genus minimizing in B4. And that's the content. I should at least drop the two names of the people who proved it. This is Cronheimer and Mrovka's result from '94 using gauge theory, Cyberwitten.
Thank you.
Other question? The microphone is not spiking you. Okay, so let's type again.